All right, we want to do another problem, and this problem is to find the settlement at t equals infinity beneath both the center and the edge of this structure. If you notice, it has a basement of 3 meters. The width is 15 meters. The weight of the structure is 50,000 kilonewtons. We have gravel over silt. The water table is there. The base of the silt layer is at 70 meters. This is the t equals 0 minus figure. This is the t equals 0 plus, the t equals infinity figure. The soil properties are here. Gamma D, gamma saturated, C epsilon R, C epsilon C, and the OCR are given. And what I want you to do, I laid this out so that you can solve this, is to basically fill in the blanks here. The depth of the bottom of the pressure bulb, the depth of the top of the silt, so I'm helping you out, depth of the point of interest, and H, you can compute all those. And once you've done that, you can get the Z sub F over B. You need to get the pressure bulb factor for that value of Z sub F over B below the center and also below the edge. Get those, and then what I want you to do is to basically fill in the table for the center, fill in the table for the edge. So you've got this table to fill in, this table to fill in, and I've also helped you out a little bit by guiding you. That's step 1, step 2, step 3, step 4, step 5. Same process here. So what I want you to do is pause the video and solve this problem. Okay, I'm going to assume that you've solved it, and this is the solution that we have. Let's start with the pressure bulb. So the width is 15 meters. So I'm going to draw my pressure bulb here, and that is then 2 times 15 meters. It's 30 meters. That takes, now notice the pressure bulb goes not from the ground surface, but the base of the basement of the structure, base of the structure. So that's where we measure the 30 meters from. So this is at 3, the base of the structure is at 3, we have 30 meters. That means the bottom of the pressure bulb is going to be at 33 meters. So there's my 33 meters there. The depth to the top of the silt is, that's easy, you just read it off there, it's 8 meters. That means that I use these two numbers. Take the average of the two, 20.5 meters, that's the depth of my point of interest, and subtract the two numbers, subtract one from the other number. I get my H, it's 25 meters. So that means my point of interest at 20.5 meters here, that means that my Z sub F is 20.5 minus 3, 17.5 meters. That's my Z sub F. That's the distance from the base of the foundation to the point of interest, 17.5 meters. My ZF over B, I simply divide by that number by 15. And it's the same for both the center and the edge, 1.17. I'm not going to go through it, but you can go into the pressure bulb. Below the center, I get 0.28 contour, approximately. Beneath the edge at the 0.21 contour, approximately. So I now have my pressure bulb factors To get my Q, the weight of the structure is 50,000. The weight of the soil removed in the basement is the volume, which is 15 squared times 3, times the unit weight of the gravel, which is 21. And then we divide all that by the 15 squared, the area of the footprint. I get my Q is 159 kilopascals. I do the chart, and again, at t equals 0, well, first the depth of my point of interest is 20.5, both situations. At t equals 0 minus, my u excess is 0. At infinity, it's 0. 0 minus 0, infinity 0. And then to get my at 0 plus, that's the hard one. Well, I take my pressure bulb factor, which is 0.28, times my Q, which is 159, there. And then down below, my pressure bulb factor is 0.21. The Q again is 159. So I get 44.5 for the center, 33.4 for the edge. And U water table, you can all get that. Sum those two to get the U. To get the sigma V at t equals 0 minus, well, I use this figure. There's my point of interest. So I've got gravel, I've got silt. So I have 8 meters of gravel. 8 times 21, I've got 12.5 meters of, so there's the 21, 12.5 meters of silt, 12.5 times 18, I get my 393 for my sigma V. We have the U, so sigma V minus U gives me sigma V prime, I get 270.5. And it's this 393 and 270.5 is the same for the edge. It's no different. And then, of course, what do? I do from there to there. They've got to be the same. There to there. They've got to be the same. Then I use sigma V prime. The sigma V prime plus U gives me that. Sigma V prime plus U gives me that. Then I know that the sigma V at t equals 0 plus and the sigma V at t equals infinity are the same. T equals 0 plus, t equals infinity, they're the same, so I just can duplicate those, and then once I know that, then I can take sigma V minus U gives me sigma V prime, sigma V minus U gives me sigma V prime. So I've got all my sigma V primes. I have my sigma V prime I, my sigma V prime F, and then the OCR gives me the sigma prime P. Those are the 3 numbers I need. And what are they? Here they are. Sigma prime I, sigma prime F. Well, what's my sigma prime P? Well, NC means what? That tells me that the OCR equals 1. If you remember, you need to know NC means normally consolidated. It means that the greatest stress on the soil is the stress that exists now. The greatest effective stress is the effective stress that's on it now, which is sigma prime I. So, in other words, 270.5, that is my sigma prime P. That means that my sigma prime P is there, my sigma prime I is there. I put down the sigma prime F. That means I only use the second half of the equation, the C epsilon C. I'll use only, and here I'm going to, what 315 over 270.5. 303.9 over 270.5. And then I'm using my value of C epsilon C. And that's it. Plug those in. Those are my epsilon V's. And then we've computed our H. Our H is 25 meters. So the delta H is what? That times 25. My delta H is going to be 0.0157 times 25. And I get my settlements at the center and the edge. And then, last little part, what is the differential settlement is okay for a 1 over 300 limit. And what do we find? Well, the differential settlement is the difference between those two, 0.513 minus 0.392, 0.1205. L is the horizontal distance, half of B, which is 7.5. And we get that rho over L is going to be 0.0161, which is 1 over 62.2. It fails. So in other words, the settlement is too much. And what is the solution? Well, one solution possible is to put in a deeper basement. Okay, I want to make a little comment here about our basement and some issues. Suppose this is my situation where I've got gravel, clay, and notice my water table is up here. And suppose I want to put in a basement that is going to go below the water table into the gravel. Well, here's the problem with that. From a practical standpoint, what can happen is that this water will go into our excavation, and we can't work underwater in this particular case. So we end up with our excavation being filled with water. We don't want that. So what do we have to do if that's from a practical standpoint? Well, this is our t equals 0 minus situation. What do we do? Well, we can drive sheet piles, for instance, into the ground. And I'm not showing the whole process, but then what can we do? We can excavate part way down to approximately the water table, and we should be fine. But when we want to dig deeper than that, what do we have to do? Well, one way to do it is to put in wells around the excavation and pump water out of the wells. And the purpose of pumping the water, and hopefully you can do this, is to lower the water table. So the water table is no longer flat. It's going to look like that. Now, it depends on what the permeability of the gravel is, but that is a way that we can then create a dry situation in which we can excavate the basement. So that's one way to do it. There are other ways, but that is a practical problem that you need to be aware of. All right, stop.